Afternoon, my name is Abraham Flores. I am a PhD student in the Computational Science program. My advisor is Dr. Kenneth Nolet. Today I'll be giving you a brief tour of variational Monte Carlo calculations of neutron scattering from tritium. Few people have attempted to compute ab initio models of nuclear collisions. This is mostly due to the fact that it's quite computationally intensive. The vast majority of ab initio computations have been calculations of bound states because those have the easiest boundary conditions. Having ab initio models of all nuclear properties is a major goal of the field, simply meaning models starting from realistic protons and neutrons. This is still not achieved for most types of nuclei. VMC has been successful and is a viable starting point in more successful methods for computing bound state wave functions in nuclei lighter than carbon. VMC avoids working on a large basis of orthogonal functions by instead computing correlations between pairs of nucleons from their interaction and building those pair correlations into an elaborate guess wave function. The cost is that those integrals have to be computed by Monte Carlo methods. We start with a correlated trial wave function and optimize its input parameters variationally by minimizing its energy with respect to an interaction potential that describes two-body scattering as well as 3 and 4-body bound states accurately. We use the COBOL algorithm to perform the optimization. The difference between collisions and bound state problems is the boundary condition on the wave function. Bound wave functions have to go asymptotically to zero where nucleons are far apart, but in collisions, the boundary condition matches the wave function onto a sum of incoming and outgoing waves. In order to use VMC to compute collisions, we restrict the location of the scattering neutron so that it stays inside a surface at a fixed 9 Fermi distance from the triton's center. We use the wave function's derivative across that surface as our boundary condition. The scattering probability is a known function of the energy and the surface derivative. To generate the dependence of scattering on projectile energy, we compute separate wave functions for various boundary conditions and map out the scattering probabilities as a function of the minimized energies. The direct method works fine for single channel collisions, that is, collisions that retain the same angular momentum quantum numbers throughout the collision. In collisions involving multiple channels, the wave function needs a separate boundary condition for each channel. And after computation, it has to be decomposed into the channels because the channel amplitudes at the surface are needed to compute scattering probabilities. That outer part of the wave function also is hard to sample as well and unable to take advantage of the short range pair correlations that are mainly responsible for the accuracy of VMC. But fear not, it can be shown that those surface amplitudes can be computed through integrals over the short distance part of the wave function where the particles all interact with each other. This avoids the pitfalls of the direct method. The integral method uses the most accurately constructed part of the variational approximation to the wave function. The integrals explicitly contain the nuclear interaction potential, so we aren't just relying on the accuracy of the variational onsets. An additional advantage is that since the scattering probabilities are computed from ratios of the amplitudes, the difference between our variational wave function and true wave function appears in both numerators and denominators of those ratios and partially cancels out. Here we have two figures comparing the direct and integral methods, the left figure being the part of the wave function consisting of a separate neutron and triton with zero total angular momentum, the right being a convenient and widely used parameterization of the scattering probability called the phase shift, also for zero total angular momentum. There's a neat trick that is not obvious for the integral method in our VMC framework. We have found that we can avoid generating separate wave functions at every projectile energy by adjusting a single input parameter of the integral. Each line in the left figure represents the overlap of the 4-body wave function onto the neutron-triton space with a different projectile energy. This simple scheme greatly reduces both the human and computer work necessary to map out the phase shift as a function of the energy. The difference in the dotted and solid lines in the figure on the left represent the fundamental differences between the methods. The solid black line in the figure on the right is our empirical expectations. The improved accuracy of the phase shifts on the right figure demonstrate the computational gain from the integral method. In summary, we have developed a method for extracting scattering information from wave functions that plays more to the strengths of our computational approach by focusing on the wave function interior and takes advantage of some cancellation of errors. We are moving toward publication once we examine more angular momentum states and compute results for one alternative model of nuclear forces. Thank you for spending the last 5 minutes with me. You have a wonderful day now.